So one of the things that goes wrong when you try to actually run gradient descent on a complex network with a lot of data is that you can get stuck in these local minima. And then you start to wonder, boy, is there some other way that I can optimize these weights? I'm trying to find a set of weights for the neural network that, well, that what? That tries to minimize error on the training set. And so gradient descent is one way to do it, and it can get stuck. But there's other kinds of advanced optimization methods that become very appropriate here. And in fact, there's a lot of people in machine learning who think of optimization and learning as kind of being the same thing, that what you're really trying to do in any kind of learning problem is solve this high order, very difficult optimization problem to figure out what the learned representation needs to be. So I just want to mention in passing various kinds of advanced methods that people have brought to bear. There's things like using momentum terms in the gradient, which basically where the idea in momentum is as we're doing gradient descent, so imagine this is our error surface, we don't want to get stuck in this little bowl here. We want to kind of pass all the way through it to get to this bowl. So maybe we need to just, continue in the direction we've been going. So instead of, think of it as a kind of a physical analogy. Instead of just going to the bottom of this hill and getting stuck, it can kind of bounce out and pop over and come to what might be a lower minima later. There's a lot of work in using higher order derivatives to better optimize things instead of just thinking about the way that individual weights change the error function to look at combinations of weights, Hamiltonians and whatnot. There's various ideas from randomized optimization, which we're going to get to in a sister course that can be applied to make things more robust. And sometimes it's worth thinking, you know what, we don't really want to just minimize the error on the training set. We may actually want to have some kind of penalty for using a structure that's too complex. I mean, when did we see something like this before, Charles?
When we were doing regression, and we were talking about overfitting.
So that's right. It came up in regression, but something similar will also happen in the decision tree section.
Sure, we had an issue with decision trees where if we let the tree grow too much to explain every little quirk in the data, you'd overfit, and so we came up with a lot of ways of dealing with that, like pruning, not going too far deeply into the tree. You can either do that by filling out the tree and then backing up so you only have a little bit of small error, or by stopping once you've reached some sort of threshold as you grow the tree out. That's really the same as giving some kind of penalty for complexity.
Yes, exactly. Right. So complexity in the tree setting has to do with the size of the tree. In regression, it had to do with the order of the polynomial. What do you suppose it would mean in the neural net setting? And how would you predict what negative attributes it might have? So what's a more or less complex network?
Well, there's two things you can do with networks. You can add more and more nodes, and you can add more and more layers.
Good. So the more nodes that we put into a network, the more complicated the mapping becomes from input to output. The more local minima we get, the more we have the ability to actually model the noise, which brings up exactly the same overfitting issues. It turns out there's another one that's actually really interesting in the neural net setting, which I think didn't occur to people in the early days, but it became clearer and clearer over time, which is that you can also have a complex network just because the weights are very large. So same number of weights, same number of nodes, same number of layers, but larger numbers often leads to a more complex network and the possibility of overfitting. And so sometimes we want to penalize a network not just by giving it fewer nodes or layers, but also by keeping the numbers in a reasonable range. Does that make sense?
Makes perfect sense.